right now, if you take ibuprofen for a cranky knee, you might actually be destroying the very molecule your body desperately needs to regrow cartilage.
Which is wildly counterintuitive.
Right. It is a massive biological paradox, and, well, it sits right at the center of the deep dive we're doing today. Welcome. We are exploring a genuinely paradigm-shifting 2025 research paper from the journal Science that takes aim at osteoarthritis.
And this is not some, fringe issue.
No, not at all. It affects 1 in 5 adults. That is over 33 million people in the U.S. alone. And for decades, the medical consensus on articular cartilage has been deeply, deeply pessimistic.
Very much so.
It's an avascular tissue, meaning no blood supply, and it lacks a ready reservoir of stem cells. So the dogma has always been, once you grind it away, it is gone forever.
And the current standard of care reflects that pessimism completely. I mean, we just manage the symptoms.
Just delaying the inevitable. Right. We prescribe weight loss, physical therapy, maybe corticosteroid injections to sort of blunt the inflammation. And eventually, when the bone is literally grinding on bone, an orthopedic surgeon goes in, hacks out the joint, and installs metal and plastic components.
Because we have 0 FDA-approved drugs that actually target the root cause.
Exactly. Zero disease-modifying osteoarthritis drugs, or DMOs.
Yeah.
Nothing stops the structural degradation, let alone reverses it. But this research fundamentally challenges that assumed limit.
They didn't just slow it down.
No, they didn't just slow down joint degradation. They actually managed to induce the regrowth of lost cartilage.
Okay, let's unpack this. If we are operating under the established fact that articular cartilage inherently lacks the cellular machinery to heal itself, finding a way to force regeneration means we first have to understand what is uniquely hostile about the joint environment. Like, how did the researchers isolate the barrier to healing? Well, they started by looking at the microenvironment of the joint to find out what changes as we age or, experience trauma. And they identified a central villain. It's an enzyme called 15-PGDH.
15-PGDH.
Right, 15-hydroxyprostaglandin dehydrogenase. Now, 15-PGDH is categorized as a gerozyme.
A gerozyme. So breaking down that prefix, we're talking about an enzyme that directly drives the aging process in tissue, rather than just being like a passive bystander.
Yeah, the data takes that a step further, actually. It isn't just associated with aging. Its dysregulation actively accelerates the tissue decay.
Oh, wow.
See, in a healthy, youthful state, if you experience a minor mechanical stress, your body generates a transient, short-term inflammatory and reparative response to handle it.
Which is normal.
Completely normal.
Okay.
But as tissues age, or if they suffer a massive acute trauma, 15-PGDH becomes chronically upregulated. It shifts from being a temporary regulator to a permanent fixture. It establishes this chronic, localized injury signal that severely suppresses tissue repair.
So it's actively sabotaging the environment. And if I'm reading the biological pathway correctly, it does this by specifically targeting PGE2, prostaglandin E2. And PGE2 is heavily involved in tissue maintenance and repair signaling, right?
Right. It is the primary fuel for the regenerative engine here. Your body absolutely relies on a specific local concentration of PGE2 to maintain the extracellular matrix of the cartilage.
But the gerozyme gets in the way.
Exactly. The 15-PGDH gerozyme specifically metabolizes and clears out PGE2. It acts like a biological vacuum, constantly degrading this pro-regenerative molecule before it can even bind to the appropriate cellular receptors and do its job.
I picture articular cartilage sort of like the brake pads on a car. The traditional view of osteoarthritis is that it's just passive wear and tear, over tens of thousands of miles. And eventually you hit the metal rotor and need a mechanic to replace the whole assembly.
The joint replacement.
Exactly. But what this paper suggests is that 15-PGDH acts more like a faulty brake caliper. It gets jammed, and it actively grinds the pad away far faster than normal mechanical friction would, purely because the biological machinery has become dysregulated over time.
That is a perfect analogy. And what's fascinating here is that the paper's in vivo models perfectly illustrate that active grinding process.
How so?
Well, the researchers wanted to see exactly when and where 15-PGDH spikes. So they looked at naturally aged mice, animals older than 24 months, which is basically the equivalent of a senior citizen.
Right.
And in these mice, the 15-PGDH levels in the knee joints were exceptionally high. But then they look at a completely different model. Young, healthy adult mice that had just suffered a surgical destabilization of the medial meniscus.
Basically a massive traumatic joint injury.
Exactly, mimicking an ACL tear in a young human athlete.
Which we know clinically is a huge risk factor for early onset osteoarthritis. Like you blow out your knee at 20, you often have full-blown arthritis by 40.
Yes. And the tissue analysis explains exactly why. In those young, traumatized joints, 15 PGDH spiked to the exact same destructive levels seen in the naturally aged mice.
Wait, really? The exact same level?
The exact same. So whether the joint is degrading from decades of use or thrown into chaos by an acute traumatic injury, this gerozyme emerges as the common denominator. It effectively sterilizes the joint's regenerative capacity.
So if 15 PGDH is the faulty caliper grinding away the tissue, the obvious intervention is to chemically unstick the caliper. What happens when we completely block this enzyme's activity?
Well, the research team utilized a highly targeted small molecule inhibitor. They refer to it as PGD-high. And they designed the trial to address both models of the disease we just talked about.
The old mice and the young injured ones?
Right. For the aged mice suffering from age-related osteoarthritis, they administered the inhibitor systemically for a month. For the young mice with post-traumatic osteoarthritis, they used localized intra-articular injections directly into the knee capsule.
And the structural results were mapped using ORSI scoring, which is the standard histological assessment for cartilage degradation.
Right. A high ORSI score means deep clefts, fibrillation, and complete loss of the proteoglycan matrix.
Bad news, basically. But the inhibitor didn't just stabilize the scores, it reversed them. The treated mice regrew thick, structurally sound cartilage. Here's where it gets really interesting, though. But wait, how do we know this new cartilage isn't just cheap biological duct tape?
What do you mean?
Like, when cartilage usually tries to heal, it lays down fibrocartilage. It's that tough, low-quality scar tissue. Is this new growth that rigid scar tissue, or is it the real deal? Real shock-absorbing hyaline cartilage?
It is absolutely the real deal. The immunohistochemical staining confirms they completely bypass the scarring phase.
Really? No fibrocartilage at all?
Right. Fibrocartilage is characterized by type 1 collagen, which is rigid and fibrous. But true articular hyaline cartilage is defined by a highly specific extracellular matrix composed of type 2 collagen, aggrecan, and lubricin.
And that's what they found.
Exactly. When they stained the newly regenerated tissue in the treated mice, they found dense, uniform expression of COL2 and aggrecan, alongside the boundary lubricating protein lubricin.
Oh, wow. So it wasn't a biological patch job. It was the de novo generation of pristine, functional hyaline cartilage.
But wait, we have to talk about how they measured the subjective experience of the mice, because pain is entirely subjective.
It's the hardest thing to quantify.
Right. You can't just ask a mouse if its knee throbs when the barometric pressure drops. How do they rigorously quantify joint relief without just relying on a human guessing if the mouse feels better?
Measuring nociception and functional recovery in quadrupeds is notoriously difficult, yeah. So the researchers deployed a triad of objective biomechanical assays. First, they used a catwalk gait analysis system.
Which is like a treadmill with cameras.
Sort of. The mice run across an illuminated glass plate equipped with high-speed cameras. The software maps the exact surface area and dynamic pressure of every single footfall.
Oh, because an arthritic mouse will favor the injured limb. Exactly. They reduce contact time and peak force. But the imaging showed that mice treated with PGDI-high actually restored their gait symmetry. They were putting full physiological weight on the previously injured joints.
So that handles the biomechanical loading. They're literally walking normally. What about the neurological sensitivity, the pain itself?
They addressed that with the Von Frey assay, which measures mechanical allodynia, essentially testing neuropathic pain hypersensitivity.
Poking them with little filaments.
Yes, calibrated microfilaments applied to the bottom of the paw. Arthritic mice develop a hypersensitized pain response to even the lightest touch. But the treated mice return to baseline thresholds.
Incredible.
And finally, they use a pressure application measurement, or PAM assay. This applies quantified direct mechanical force to the knee joint itself until the animal exhibits a withdrawal reflex.
So directly squeezing the bad knee.
Right. And the PGDI-treated group tolerated significantly higher compressive forces, entirely comparable to uninjured, healthy controls.
Which brings us back to the most perplexing biological question of this entire study. If there are no stem cells dividing and making new cartilage, if we know articular cartilage is largely post-mitotic, where is this pristine new tissue coming from?
Answering that required stepping away from traditional histology and moving into advanced transcriptomics. The researchers utilized single-cell RNA sequencing combined with codex.
Okay, break that down for us. Bulk RNA sequencing is like throwing a tissue sample into a blender, right? You get an average readout of gene expression for the whole smoothie.
Exactly. Whereas single-cell RNA sequencing lets you look at the exact gene expression of every individual cell, like inspecting every single piece of fruit before it goes in the blender.
And Codex adds the spatial dimension. It's highly multiplexed imaging that gives you the exact GPS coordinates of those specific cells within the intact tissue architecture.
Exactly that. By overlapping the transcriptomic data with the spatial maps, they look for markers of cellular proliferation. Markers like Ki67 that indicate cells are actively dividing.
And what do they find?
They found practically zero.
Zero.
The PGD-high treatment was not triggering cellular division. The cells were not multiplying. Instead, the existing cells were undergoing a massive phenotypic shift. They were fundamentally changing their identities.
Wait, so if they aren't dividing, the existing cells are basically rewriting their own job descriptions?
Yes. The data revealed a pathological cellular state in the arthritic joints. They found a massive expansion of a specific subpopulation of cells marked by the surface protein CD200.
Okay, what are those?
These are hypertrophic chondrocytes. In a healthy joint, chondrocytes quietly maintain the cartilage matrix. But these CD200-positive cells have become deeply confused. They are actively upregulating gene pathways associated with endochondral ossification.
Ossification, meaning they are actively trying to mineralize the cartilage and turn it into solid bone.
Exactly. And not only are they trying to calcify the tissue, but to do so, they secrete matrix metalloproteinases. These are enzymes that aggressively chew up the surrounding cartilage to make room for bone.
So they're the ones destroying the joint.
They are the primary drivers of the structural decay. But after treatment with the PGDI inhibitor, the spatial transcriptomics showed this toxic subpopulation of CD200-positive cells plummeted from 8% of the tissue down to just 3%.
A massive drop.
Huge.
Yeah.
And concurrently, the population of healthy, matrix-producing articular chondrocytes, the cells doing the actual maintenance, doubled from 22% to over 42%.
So it's not like hiring a bunch of new, young workers to fix the factory. It's more like taking the existing, grumpy, burned-out workers who are actively breaking the machines, sending them on a wellness retreat, and bringing them back fully recommitted to their original jobs.
That's a great way to put it. And if we connect this to the bigger picture, that retreat, that software reset, is driven by epigenetic reprogramming.
How does that actually happen inside the cell?
The researchers noted that following the inhibition of 15-PGDH, there is a massive upregulation of a master transcription factor called SOX9. Right. SOX9 is the critical lineage-specifying factor for chondrogenesis. By turning SOX9 expression back up, the treatment effectively overwrites the pathological bone-making instructions. It forces the confused cells to remember their true articular identity and resume pumping out healthy type 2 collagen.
Okay, I need to stop you here. I need to push back on a massive pharmacological contradiction here.
Sure. What is it?
You mentioned earlier that blocking the Gerazyme 15-PGDH works because it increases the local concentration of PGE2, the prostaglandins, in the joint.
Right.
But anyone who has ever taken an NSAID like ibuprofen, naproxen, or celecoxib knows that we take those specifically to block prostaglandins because they cause inflammation and pain. So why are we trying to save PGE2 here? Isn't that functionally backward?
It absolutely sounds backwards at first glance, and it exposes the ibuprofen paradox that really plagues modern orthopedics.
The ibuprofen paradox.
Yes. The critical missing context in traditional pain management is the difference between systemic cascades and localized physiological signaling. It is entirely about the volume dial.
Meaning the dose makes the poison.
Essentially, when you have an acute injury or a massive systemic infection, you get a systemic massive spike in PGE2. That drives pathological inflammation, swelling, and acute nociception. NSAIDs indiscriminately nuke that entire pathway to provide relief.
Okay, that makes sense for acute pain.
It does. But what this paper demonstrates is that maintaining a localized physiological baseline of PGE2 within the vascular boundary of the cartilage does the exact opposite.
So by just indiscriminately popping over-the-counter painkillers, we might be silencing the immediate pain, but we're simultaneously stripping the joint of the baseline, signaling it fundamentally needs to heal.
Exactly. We are trading short-term comfort for long-term structural destruction, and the cellular data completely supports that concern.
Did they measure the inflammation levels when they boosted PGE2?
They did. When the researchers boosted PGE2 locally by inhibiting the Gerazyme, they did not see a spike in inflammatory markers. In fact, they saw a dramatic reduction in pro-inflammatory cytokines that are known to drive osteoarthritis pathogenesis.
Like what?
Molecules like CCL7, CXCL10, and IL-2 all plummeted. The localized PGE2 was actually acting via specific receptor pathways as a pro-regenerative anti-inflammatory signal.
That is just a staggering implication for how we approach sports medicine. But we have all seen miraculous mouse models that fail completely the second they hit human biology. Mice are highly regenerative by nature.
They are.
A human knee that has been grinding away for 60 years is a completely different biochemical environment. How did the team prove this mechanism works in humans?
They bridged that gap by going straight to the most hostile human tissue available. They partnered with orthopedic surgeons who were performing total knee arthroplasties on patients aged 55 to 75.
So these were patients with end-stage grade 4 osteoarthritis.
Yes.
Literally the worst of the worst. Tissue that had structurally failed so completely it was surgically cut out and thrown in the biohazard bin.
Exactly. They took these discarded human cartilage explants, placed them in a vascular ex vivo culture, and treated them with the PGDI inhibitor. And the exposure time was just 1 week, 7 days.
Just 1 week. That is an incredibly short window for endovascular tissue to show any meaningful change.
It is. And yet the human explants mirrored the in vivo mouse models almost perfectly. Within 7 days, that toxic population of confused CD200 positive cells significantly decreased.
Wow.
And the healthy glycosaminoglycan content, the GAGs that give cartilage its water-retaining cushion, measurably increased. They even subjected the human tissue to mechanical testing to measure Young's modulus, which assesses the actual physical stiffness and elasticity of the material.
So they were testing the actual physical biomechanics, not just looking at cellular markers on a slide.
Exactly. The physical mechanics of the human cartilage demonstrably improved. The tissue became firmer and more resilient.
In 7 days.
In 7 days. Furthermore, the transcriptomic analysis of the human explants revealed profound metabolic reprogramming. The pathways associated with matrix degradation and ossification were downregulated, while pathways for glycan synthesis and oxidative phosphorylation just surged.
Oxidative phosphorylation, meaning the cells were completely overhauling their metabolic engines to handle the massive energy demands of making new cartilage. They were waking up.
They were actively rejuvenating. The fact that end-stage, discarded human tissue, totally devoid of a blood supply, could mount this profound regenerative response in just 7 days. It proves the intrinsic plasticity of human chondrocytes.
They still know how to heal.
Exactly. They retain the capacity to heal. They're simply suppressed by the local gerasine environment. This raises an important question regarding how we currently treat joint pain versus how we should treat it.
Right.
If this pathway translates into clinical trials, we are looking at a fundamental paradigm shift. We move away from palliative care and mechanical replacement and step into true disease modification.
So what does this all mean? Let's trace the arc of this deep dive. We started with the grim biological dogma that articular cartilage is a depreciating asset. Once you wear it down, you are basically on a one-way track to a titanium knee.
Right.
But this paper dismantles that inevitability. By unmasking 15-PGDH as a localized gerazyme that siphons away the regenerative fuel of PGE2, the researchers found a highly specific target.
And a highly specific solution.
Exactly. By blocking that gerazyme, they didn't have to rely on injecting foreign stem cells or, highly engineered scaffolds. They simply allowed the natural accumulation of local PGE2 to initiate a massive epigenetic factory reset.
Reinstalling the original software.
Yep. The existing, confused, bone-making cells were reprogrammed back into functional articular chondrocytes, laying down pristine type 2 collagen. And crucially, it worked in end-stage human tissue in a matter of days. It means we are looking at a near future where an ACL tear in your 20s or an aching knee in your 60s might just require a localized disease-modifying injection to truly cure the joint, saving millions from total joint replacement surgery.
And that leads to a much broader, perhaps even more profound consideration for the field of aging research as a whole.
Oh.
Yeah. We have just seen empirical proof that this specific gerazyme acts as a highly localized aging accelerator in knee cartilage. And the blocking it literally reverses the biological clock for that specific microenvironment.
Okay, I see where you're going with this.
Right. So if 15-PGDH is acting like a faulty, destructive brake caliper in our joints, we have to ask what other biological systems are failing right now, purely because of a localized gerazyme.
What other brake pads are we wearing down?
Exactly. We know from other literature that 15-PGH is significantly elevated in aged skeletal muscle, cardiac tissue, skin, and the colon. What happens to human longevity when we stop treating aging as an unstoppable systemic whole-body decline and start treating it as a series of localized, completely reversible molecular injuries?
That is a staggering thought to leave on. The idea that aging isn't necessarily a cliff we inevitably fall off, but rather a collection of jammed molecular signals that we are finally learning how to unstick. Thank you so much for joining us on this deep dive. Go give your knees a stretch, maybe think twice before aggressively reaching for that bottle of ibuprofen, and keep questioning what you think is inevitable. Catch you next time.